So yeah, okay. So everything I should say, yeah, okay, I can get accountable for whatever I'm going to say now. So yeah, so what I've just said is we're working indeed on quantum antibody systems, finite size systems, so molecular systems, like the electronic structure problem, and we're looking at that from different sides. So you can see them over there. So probably what landed me the job was work I did also together with Paul Johnson, who's here in the audience, on geminal theory. But we're also working now on ideas from other ideas that are coming in from physics, like tensor network methods, symmetry breaking, going to talk about today. We're also looking into how we can understand a little bit on the electronic structure problem from a machine learning point of view. Quantum computing is also something we are, and the algebraic angle is there, very interesting to us, and also looking into out of equilibrium systems. But today I'm mostly going to be talking about symmetry breaking. So this is work I've not done alone. So this work has originated from when I was back in Ghent in Belgium. So you may recognize Patrick Bulting, Guillaume Akke, professor and research associate in Ghent University. Xeno, who's started his PhD recently, is a good coder as well. So basically, he got all the bits and bytes together to get this thing running, our project. Hugh Burton is a brilliant chemist, theoretical chemist at the University of Oxford right now, has very nice and very unconventional and refreshing ideas in terms of electronic structure theory and understanding it in the fundamentals of that. And last but not least, Amir. Amir is working with me here at UMB, PhD student, brilliant PhD student as well. Amir is now looking into the symmetry breaking part, which may appeal to the, let's say, more the condensed matter or physicist in the audience. Okay. So here is an outline of the talk. So I've broken it down into three components. So the first one is more for to get everybody on the same page, especially also those who are not too familiar what quantum chemistry and theoretical chemistry is, what that has to do with quantum. So that is the first part. Second part, I'm gonna introduce, well, I'll talk about the method that we call constraint configuration interaction, which allows us to get a little bit more insight into some of the methods that we are developing and approaches that we're using. And in the last section, if we get there, I'm going to talk about the generator coordinate method. Again, a method that originates from physics, is based on ideas of broken symmetries, and I'm going to show you how we can potentially use that as a new method for electronic structure theory. Okay, so let's get started. So why we do what we do. So why are we still doing theoretical chemistry and quantum chemistry? Well, the reason, well, it's not the only reason, but there are two good reasons here on the screen. So on the left-hand side is a biomolecular compound. It's a protein, and the protein is called amyloid beta. Now, why is this one interesting? Well, it turns out that this one is associated to Alzheimer's disease. Okay, so whenever people do post-mortem dissections on the brain tissue or the brain cells of people who were diseased from, who had Alzheimer's disease, they find that these amyloid beta proteins, they curl up in a certain manner, they aggregate such a way that they form spikes and they pierce through the to the brain cell membrane. Obviously, this is not a good way to go. It's not very healthy. So we try to understand that process a bit better, the protein folding process, as to say. So this is a very important aspect of biochemistry. On the right-hand side, if you're more technologically inclined, what is there is like one of the tiniest magnets we know. It's a Taken complex. So the orange dots there are iron atoms. They are embedded within an organic framework. And the thing is that they can act as a memory. Now, if we talk about iron, we talk about spin degrees of freedom. We talk about the quantum structure there that is very important to be able to describe that molecular magnet or predict properties of that. So getting a good handle on that is also very important with respect to the future. Now, this is, I would say, the ultimate goal. I'm pretty sure that I won't see the protein folding problem being built up from quantum fundamental, the Schrödinger, up in my lifetime, but at least I want to give the next generation the opportunities to tackle that. Okay, so where is the problem? Where is the problem in theoretical chemistry? Dirac already phrased it almost 100 years ago, right? So he wrote down the laws and he saw that it was actually impossible to do anything with it. So I'm going to read with you, okay? This is from a paper, famous paper from 1929, in which he depressingly said, the fundamental laws necessary for the mathematical treatments of large parts of physics, so high energy physics was not there yet, and the whole of chemistry are thus fully known. So basically what it says, chemistry is solved, right? And the difficulty lies only, love the only, in the fact that application of these laws leads to equations that are too complex to be solved. Okay, so that is what we're still struggling with today. Now you can ask a question, why is that? Are we just too stupid, or to solve that, or what is the issue here? Right? If Dirac couldn't solve it, then probably the answer is not in mathematical way, in the mathematical terms. Okay, so give you those who are not familiar with quantum chemistry. So here is how a typical problem is being solved. So let's say you want to have the electronic structure of, or you want to have the structure of a molecule. So what do? So first of all, you fix the nuclei. So we work in the Born-Oppenheimer approximation. Okay, so that's the first thing that we do. So we basically fix our nuclei in space. Now, each of these nuclei, they come with a set of orbitals. Okay, a set of atomic orbitals. So the typical orbitals that you know, like the hydrogen s orbitals, the p orbitals, the d orbitals, whatever, right? And those orbitals, they give you the space in which you can put electrons, right? So each orbital can only take one electron, okay, 2 electrons if you also include the spin, because of the Pauli principle, but you distribute them over all these possible atomic orbitals. Now, this is not the end, because then it only becomes interesting, because then you have to correlate all those configurations. So you have to find a method in which you know how, which you can correlate all those classical, let's say, configurations. And then once you have that, you extract your observables, the ones that you're interested in. In chemistry, for instance, typical, it's an energy, right? Because you would be interested in a energy profile that happens if you go through a given chemical rearrangement or a chemical reaction. Okay. So where is the problem? Because this sounds pretty straightforward, pretty easy. Now, the problem is here, because you rearrange, so you pick a set of orbitals, right? So let's say, which each atom you chose, let's say 5 to 10 orbitals, and then you start redistributing your electrons over all those orbitals. The number of those distributions grows extremely rapidly. Okay, so what I've plotted here on the right-hand side is the dimension of the Hilbert space, so the number of possible configurations as a function of L, and L is the number of orbitals that you include in your model. Ideally, you want to have an infinite amount of orbitals. Obviously, that's not possible for a computer, so we typically limit it to just a few. But here comes, so the blue curves here are the dimension of that Hilbert space as I give the molecules more and more orbitals to be distributed in, okay? And for a couple of compounds, so I have the hydrogen dimer, I have methane, I have iron atom there, I have benzene there as well, and my favorite molecule, caffeine, is sitting there on the right. So you see, as you increase the number of boxes, L, or the number of atoms, then it immediately, these curves, they skyrocket into the sky. Now, to appreciate that, on the left-hand side is a logarithmic scale, right? Now, for your reference, I've also put down a red curve there, which is the curve that is the number of numbers that you can store in a computer with 1 GB RAM, okay? So that means that I will always be able, so how far I stretch this the system for how many orbitals I include for the hydrogen dimer, I'll probably always be able to get my my system completely described. Whereas I take benzene, for instance, 42 electrons, I immediately go above that red curve. In other words, I'm not even able to store all the information in my computer for benzene, for the total Hilbert space. Now you can say, okay, poor guy, poor Stijn, he only has a 1 GB RAM computer. Why don't you just wait for a meaner computer that will, a few years from now, Moore's law will kick in and it will get you a meaner computer? Well, that's right. However, my red bar, I will only be able to increase with a few nudges, right? Every time I double my computer power, I'm only going to go 1 notch up. And you can see I will never be able to reach, let's say, 10 to the power of 30, because for that, I would need more computer resources than there is actually matter in the universe. So this is a losing game. So solving the electronic structure problem by just buying a meaner computer will never get us. Simply, this is the problem, what we call the explosion of the Hilbert space. It is a combinatorial problem. So it scales exponentially. Okay, so then what you do, you focus on the things that matter. Okay, so you go and look into the system and you try to, and you put on your physicist hat and you look at what is the most important correlations, what do you want to model, and then you have, then sort of a box of Pandora opens up, because there's a myriad of different ways of different types of correlations at different orders of magnitude that all compete with one another in some way, right? So we have the short range dynamic correlations. It's the electron dance among themselves. We have the van der Waals dispersion interaction, which is like a couple of orders of magnitude smaller, but still they extend them onto long range. We have single particle static correlations, what we call, which is induced by degeneracies in a single particle picture. So let's say all sorts of ways, and you can distribute magnetic spins over a molecular magnet, etc., etc. And there are a few things that we cannot use. So there's typically a lack of symmetry, right? So we cannot use translational symmetry because in a typical compound, there is no translational symmetry as in a crystal. There is no such thing as topological symmetry that can magically save or give you some interesting like subspace to look in. So sometimes we just have to deal with the problem that our system scales up, and we need to be able to treat those things in a size extensive way. That is another thing that needs to be taken into account. So this is the problem. However, people are doing a good job, right? So methods are being developed as we speak, right? So this is on the right-hand side is, I would say, a recent paper, 2020, so now it's 2 years ago, by Ericsson, who basically invited all top of their fields, state-of-the-art methods to do a energy calculation of the benzene molecule. Okay, it's 42 electrons. And then they did a blind comparison. Okay, so what is there? So there are a couple cluster methods. Marcel, there is configuration interaction, Monte Carlo configuration interaction. There is DMRG there. There is some many-body perturbation theory is there as well. And what turns out is that after a, let's say, very sophisticated calculation, they all sort of agree. Okay, so that is good news, right? So it's all good news. We have a pretty good handle on these methods after a mean, well, a very kick-ass calculation. Okay. Now, what is the bad news here is that's only for benzene, right? Benzene is sort of like one of the building blocks of aromatic systems. So if we want to look at anything that is remotely interesting to an organic chemist, we have to include a lot of those. So we're kind of stuck here. It's a depressing message that this is sort of like the end of the road for this kind of thing. Okay, but then this is not the only thing we can do. What we have is we have density functional theory. Okay, so density functional theory is almost like a miracle. Okay, what does it say? density functional theory, it says that the energy of a many-body quantum electronic system is actually completely described in terms of its density. And that is extremely good news, because now we can replace our wave functions, which is this exponential scaling object, into something that only scales into, like, it's a three-dimensional object, right? So it only scales into the 3 Euclidean coordinates, right? And by some theorems, like the Hohenberg-Combs theorem, we also know how to extract that, right? So we know that the density of the system is basically, the exact density of the system that we're after is basically given by the density that minimizes an energy density, so-called energy density functional. Right? Now, that sounds like a free lunch, and it would be if we would know what this functional is, right? So we don't know what that functional is. So people have been designing lots of wonderful functionals over the years, over the decades, and they all work pretty well. I mean, it's impressive how performant they are. However, there are a couple of, let's say, fundamental issues associated with that. And one of those fundamental issues I want to talk to you about a little bit more today, which is a delocalization error and resulting fractional charges in molecular systems. Okay. So what is given in the figure? So let's focus on the the left upper side. So what do we see there? There is a binding curve of the hydrogen dimer cation. So it's a one electron problem, two hydrogen centers and 1 electron that is going, and that is playing the dance of between those hydrogens. Now there's 3 curves there. So the red curve is the exact curve that is given by Hartree-Fock theory. Hartree-Fock theory is a mean field theory, but in this particular 1 electron problem, Hartree-Fock theory is exact. So that's the exact problem. Okay. So we see the energy curve as a function of the dissociation between the 2 hydrogens. Okay. So you typically see that the typical behavior, we have an equilibrium. So it's a low energy at, let's say, about 1 angstrom. And then as you dissociate the 2, you get to a reference energy of 0. Now, the 2 other curves that are given there are 2, let's say, very simple but fundamental density functional theory calculation. The black one is given by an LDA, local density approximation. The other one is B3, the blue one. So what you see there is that it qualitatively disagrees with what the exact result should be. Okay, and that has fundamental consequences, because what you then you go to the right-hand side. What you can do is you can look at how the charge of that electron is being distributed over the 2 centers, right? At full dissociation of the system. Now, if the system is fully dissociated, then it shouldn't matter where I put that electron. So either it's on the left-hand side or it's on the right-hand side. There's a full symmetry there that should be exploited. Now, and that is actually what Hartree-Fock theory tells us. So it doesn't matter where you put it. So you can basically choose the broken symmetry solution. You put your electron on one side or you put it on the other side. Now, if you look at what density functional theory tells us, it tells us that we get a minimum of the of that particular the variational problem at the position fractional charge 0.5. It means that density functional theory wants to cut this electron and put half of it on the left-hand side and half of it on the right-hand side. So that is, it's obviously something that's very counterintuitive. One would say it's even wrong. However, this is something that is at the fundamental level of density functional. Similar things can happen when you do the full problem. So you do the H2 binding curve, so the full dissociation of the full with the 2 electrons associated with it. Similar things happen, but then not only with the charge, but also the spin gives us a wrong dissociation profile. Okay, so what should it be, right? So if that picture is wrong, what should it be? Well, basically, the answer has been given to us by Perdue, one of the godfathers of density functional theory. The thing is that density functional theory as a function, so if I would do the energy as a function of the number of electrons that I'm putting on a certain compound, in this particular case, it's a chlorine system, the green one is a chlorine, and you put a number of electrons on that chlorine. So then density functional theory allows you to make a profile of the energy of that system as a function of how many electrons you put there and how many in a fractional sense, right? So you can basically let that vary over non-integer numbers. And why? Simply because we can do a constraint on the density, right? So we can say, okay, the density, if I integrate out over space, this must be n, and that n, number of electrons, doesn't necessarily have to be an integer. That's something that we put in. Now, how would you do that exactly? Because in an exact theory, you have to distribute electrons, and we cannot distribute fractional electrons. We have to do full electrons, okay? So then, oops. Purdue makes the argument that it should not be this convex curve, but it should be piecewise linear, right, between the integers. Okay, so how do you get there? Well, at the integers, the problem is pretty simple. Then it's a standard problem. You distribute your integer number of electrons. You put 16, 17 at 18. You calculate 3 points. You get an energy, and you have those 3 points. And as you can see, that actually does this LDA does pretty well in that particular case. So that's good. Now, how do you connect point 16, point 17, and point 18? How do I know that that should be a linear curve? Well, the argument is here, and it's spelled out in detail in this PRL paper from 1982, is you basically make ensembles, okay? So what do you do? What does it mean with that? Basically, you take a chlorine in this particular case, and you copy it. You make as many copies as you can approximate a fractional number, as you need to approximate a fractional number, and you put them at infinite distances, all apart from each other, okay? And then you assign so many, let's say, electrons there, okay? So 16 on this one, 16 on the other one, 17 on this one, 17 again on this one, 16 on that one, such that if you average out over the ensemble, you'll get a number of electrons that corresponds to your fractional number that you okay? So obviously, if you average out over independent things, then you're definitely going to get to something linear, right? So the argument is a little bit dodgy, but one could buy into it. Okay, so the purpose of this presentation is to tackle that problem, or reobtain that piecewise linear behavior in a little more rigorous way. Okay, so I came in. This is so I came in actually not. I'm not a DFT expert actually. Some people may already figure that out, but I came in from a different direction. So when I joined the chemistry community, I was very much interested into this optimization of the variation optimization of the two-body reduced density matrix. The idea is very simple. You have, if you look at the energy, it is basically a trace over the two-body density matrix, because Coulomb interactions, they are two-body, and then you try to optimize at 2 dm. You try to optimize the energy with respect to the 2dm, and then you hope to get to the correct result. Now, this approach, wonderful how it sounds, is plagued by the so-called n-representability problem, in which you have to put constraints on the wave on the density matrix such that it obeys good physical properties. And in some sense, it has a similar problem, because it's a 2RDM. So it's a reduced density matrix. It's a density matrix, a density matrix method. And we basically see the same problems, right? So if we dissociated the NO plus diatomic, and we dissociated that, and we saw that the optimal place was actually at a fractional charges solution, and in which we would put like 0.53 electrons on the oxygen and 0.47 of the electron on the nitrogen, which is obviously clearly wrong. So this is something that is not only DFT. Everything that is density, and every density method is basically plagued with the same kind of issue. Okay, so how did we try to shed some light on this problem? We did that by doing constraint configuration interaction. What is constraint CI? I think the original formulation of a constraint configuration interaction was done by Dirac himself, but it was only introduced in 1963 by Mukherjee and Karplus. And it was used at the time to fix erroneous dipole moments in unrestricted variational theories. Okay, so let's say you have an H, a Hamiltonian, and you have a variational theory. Then you want to lower your energy as much as possible, such that you will get to the exact answer, the exact number. Now, how can you do that? One way to do that is by breaking symmetries, right? Spin symmetry being one of them, or spatial symmetry being one of them, or whatever. Okay. And now what happens when you do those things? You induce unphysical effects, right? So your wave function will not represent the physics very well anymore. Eh? So you get a good energy, but at the cost of the wave function. So what Mukherjee and Karplus decided to do is whether they could still do this unrestricted symmetry broken variational theory, however, with putting some constraints on the observables of interest. In this particular case would be the dipole moment, right? So let's do an unrestricted Hartree-Fock calculation, let's say, such that our dipole moment still has the experimental value that we want. Okay, so we decided to do something similar, however, a little bit different. Now, how can we use this idea now to look at this fractional charge problem? Well, let's say we do the following. So we add to our system, we add another system, okay, and let's say a copy, and we let it interact, okay? Then we have a system A and a system B, and the system B then acts sort of like a bath, okay? Now, like in a dipole, in a dimer, one of the atoms can act basically as system B or as the bath for the other one, correct? Okay, now if I do that, I would run up exactly in those issues that I had with this V2 RDM, right? In which I would dissociate my nitrogen, oxygen, nitrogen oxide, and then would get to fractional charges. So I don't want that. So I want to find the solution such that I can find that I have a knob such that I can tune how many electrons that I'm putting on the left-hand side or on the right-hand side, such that I can do that scan as a function of particle number or fractional particle number. How do I do that? Well, I have my Coulomb interaction there, and what I add is a population operator, a Mulliken projector. I mean, you can add in different for the quantum chemists in the audience, and you add a chemical potential. Okay, so you basically dress this Hamiltonian with a constraint on how many electrons you're going to put on system A. And then what we did is we did the exact theory. So we did a configuration interaction, full configuration interaction in well, a good basis, let's put it this way, right? And the single value decomposition of the system tells me that I can dissociate, or I can decouple. Well, not really decouple, but I can write this as an entanglement between system A and system B. Okay, so that's exactly what we did. And here are the results for a couple of, well, let's say fundamental and simple and understandable system. It's chains of hydrogens, one after the other. So H2 is the one, probably the only one with any chemical relevance, experimental relevance. It's the hydrogen dimer. Then I have a trimer, and then I also have H4. It's just 4 hydrogens next to each other. It's not the square. And what I do, I plot the energy, okay, as a function of the constrained number of electrons that I'm putting on hydrogen number 1, right? So I have 1, 2, 3. Hydrogen, the NOS is the number of particles that I put on the left-hand side. 4 different dissociations. Okay, so for different distances between the two systems. So I have 4.5 angstrom, 6.5, and 8.5. So as I'm going from blue over orange to green, the system becomes much more dissociated, and Purdue tells us that we should go to a piecewise linear behavior. And lo and behold, this is actually exactly what you get, right? So for instance, in the H2 case, the integers, I can either have fully ionized, so 0 electrons on my left. I can either have 1 electron on my left hydrogen, or I can put 2 of them, so I can charge it. And if you dissociate it, you can see that it basically you recapture that piecewise linear behavior in a very, let's say, adiabatic way. Okay, so I mentioned that we had the Lagrange multiplier, that is a chemical potential. Okay, so what we need to do in those to reach that our tuning knob, we need to tune that chemical potential such that we reach that desired number of electrons on the system. So for a particular, let's say, calculation, you're interested in, let's say, 1.5 electrons on the left hydrogen, then our Lagrange multiplier, returning the knob such that it just goes a little bit beyond 0, and that we hit that point of interest that we want. Now, one thing that you can notice here is that you have this stepwise function, right? So our Lagrange multiplier, our chemical potential is fairly constant, and then suddenly at some point it makes a huge jump. So then we have to be very careful. This is also the reason why Xeno had to do very precise programming to nail that problem down, to really tune that. And then you get to the next step, and then you're at 1 electron, and then you tune a little bit further. You can basically like ramp up the knob, and then suddenly you have to be very sensitive again. So then it goes back up into the next plateau. But you see the stepwise behavior as it goes. So we try to understand it a little bit better. So why that situation happened? So why it happened like? Okay, so here's a cartoon of on the right-hand side of the hydrogen dimer. Okay, so I have 2 hydrogens and I put 2 electrons on. Okay. And let's say these are pretty much a dissociation. Okay, so I have one at -infinity and one at +infinity. Okay, then the middle one will be my ground state. Okay, because then I have 2 neutral hydrogens, neutral hydrogen atoms, one on the left and one on the right. If I choose to promote or move 1 electron from one side to the other side, then I go into an ionic state, right? Because then one of them is just a proton and the other one is a negative hydrogen anion. Okay, and so this is the schematic, the energy that you will get. Now, okay, so this means my ground state has 1 electron on the left-hand side. Now I want to tune my system such, I want to take my Lagrange multiplier such that I can have a variable amount of electrons C on my left hydrogen. So how do we do that? So the first thing I do is I take my Lagrange multiplier and I tune it such that the left-hand side, so the 2 electrons on the right hydrogen, and my ground state was degenerate. It becomes degenerate, right? So I'm tuning it up, right? So I'm ramping up my mu, and suddenly they become degenerate. Now I have something, right? Because now I have a situation in which I have 2 degenerate states. They both have the same energy, which means what I can do now, I can mix up these 2, right? There's a symmetry between those states. There's a degeneracy. I made that degeneracy so by means of my Lagrange multiplier. So what I can do now, I can create these 2 mixed states, psi and phi. Okay, with a mixing parameter, square root of C, square root of 1 minus C, such that the expectation value of psi, ground state, energy eigenstate, is exactly given by C. Okay, so by doing so, I can basically tune. I can I bring up my ground state, and I open up a channel, a quantum channel, such that they, by means of the degeneracy, I can redistribute these electrons as I wish. Now, if you use that psi and you do a quick calculation on the back of an envelope, you will indeed see that you recapture that piecewise linear behavior of the energy in terms of the initial energies of the integer system, and you also gain some insight into why that process is happening. Whoops, that was not the purpose. Yeah, here we are. Okay, you can also include the spin here, and then you can decide whether you want alpha spin ups or beta spins to go from one side to the other side. It makes it a little bit more interesting. It gets a little bit more more sophisticated, but the problem is basically the same. And what you can do then, you recapture the so-called Young flat plane conditions. Okay, so I don't know how much time I still have. And in the next 5 to 10 minutes, I'd like to talk a little bit about the generator coordinate method, which is the method that is in the same vein inspired. Well, it not only shows us that not only we can use the constraints as a let's say an analytic tool, but we can also use it to our advantage. Okay. And so I'm going to be talking about the generator coordinate method. But in order to talk about the generator coordinate method, what's in a name, I need to talk to you about symmetry breaking, because symmetry breaking is the driving force behind this this method. So what is symmetry breaking? Condensed matter physicists know very well what this is. Yeah? So let's say you have a magnet, okay, and a magnet is high temperature enough, so there's no magnetization, there's no magnetic fields induced by the magnet itself. And then I lower the temperature, then at some point, all the individual spins will reorganize themselves and they will choose a magnetic direction. Okay. Now, the bar, the magnetic bar, it can choose whether it goes, it puts the South Pole down, or it puts the North Pole down, right? So it has a choice to make. It can make a choice, right? And this choice is the so-called symmetry breaking. Right, so there's no symmetry anymore, right? So it has two symmetric situations. Could have either my magnet like this, or I could have my magnet like that, north to south. But obviously, it had to choose one. Okay. Now there's two aspects here. So this is a so-called second-order phase transition. It's a very interesting mechanism. However, what I want to stress here is that this picture is a typical mean field picture. Okay, so it's a mean field description. So we get a potential energy surface there, which is typically something that you get from a mean field description of a theory. And within that description, you get this, you develop these, this Mexican hat potential, in which you can choose one side or the other one. So now, if you have a mean field description, people typically think thermodynamic limit, infinite number of particles. You cannot have this in quantum chemistry, right? Where you have a finite size of particles. Now, can we have symmetry breaking in quantum chemistry? Yes, the answer is yes. We do see that. Caveat, at the mean field level. Okay, so how do we see that? We see that if we use restricted Hartree-Fock versus unrestricted Hartree-Fock. What is the difference between restricted and unrestricted Hartree-Fock? Well, the difference is just the spin degree of freedom. In restricted Hartree-Fock, we require our spin ups and spin downs to have the same description, the same molecular orbitals. Whereas in unrestricted Hartree-Fock, we don't require that, right? We don't impose that, so they can live their own ways, their own life. Okay. So basically, what happens there is you break the spin symmetry. Okay. Now, what happens if you do that? If you allow for spin breaking? So again, on the right-hand side, typical plots, it's the energy of the hydrogen dimer as a function of the distance between the two centers. And both theories, they very much agree around the equilibrium, around 1. But then at some point, when they get dissociated, it appears to be more energetically more favorable to break the symmetry. right? We call that point the Coulson-Fisher point. Okay, so the Coulson-Fisher point is a point where suddenly unrestricted Hartree-Fock is energetically much more favorable than restricted Hartree-Fock, and actually goes to the exact energy curve, right? At the cost again of having the exact wave function. Okay, so with the symmetry breaking, there's always an order parameter associated. So what we found, what you can say here is that the order parameter associated to that symmetry breaking is the spin. So yeah, that's exactly what we see. And so if you look at what the spin expectation value is at function of that bond length, as a matter of fact, so as a zero, there's no spin symmetry breaking until you reach the Coulson-Fisher point. And then for unrestricted Hartree-Fock, you see how the spin suddenly, like in it's almost like a power law there, starts to come. Okay. Now, on one hand side, so you have two pictures. You have restricted Hartree-Fock, in which you have a good wave function, so it has a good symmetry because spin is still a symmetry for a finite system, so it should have a symmetry, it should be symmetric, but it's a bad energy. And on the other hand side, I have a good energy description, but it's a bad wave function because it has spin contamination and shouldn't be there. So then came this, like I mentioned before, this brilliant theoretical chemist Hugh Burton, together with his supervisor Alex Thom from Cambridge. They said, what if we just combine the best of both worlds, right? So what if we take our restricted Hartree-Fock, we take our unrestricted Hartree-Fock solution, we mash up two, okay, so we make a linear combination of those two, and what we do is we just throw them into configuration interaction, and we see what comes out of that. And lo and behold, what you get is the red curves are the ones that the energies that are coming from this this approach, and it matches exactly with well, or very closely with the full what the full energy should be, right? So what the exact energy should be. Okay, so this sounds wonderful, particularly when symmetry can be broken, right? In the broken symmetry regime. Now, there's a little bit of a caveat there, and well, a little bit of a bummer is that if the two solutions are degenerate, then you cannot really do that because you only have the two solutions are degenerate. But they found a way to overcome that is by going holomorphic, is what they call. So they extend their solutions of Hartree-Fock into the complex plane. But it's a little bit convoluted because finding optimal solutions there in the complex plane is a bit of a hassle. Okay. So what is the difference between unrestricted and restricted Hartree-Fock? Well, like I said, there's a spin, right? Unrestricted Hartree-Fock has a spin broken, whereas restricted Hartree-Fock has a spin unbroken, right? Now, the thing with unrestricted Hartree-Fock is that you have to wait and see what comes out. So you do the calculation, and then you can say, oh, my spin is so much. Now, this is the point where a constraint calculation can, again, jump in, can be helpful. Because if we now put a constraint on that spin, we basically have a knob to tune how much of that broken spin correlations we want to include in our Hartree-Fock wave function, right? So this is what you see then on the right-hand side, right? For this is a calculation done by Amir. For different, what do we see? We see energy profile as a function of how much spin contamination, let's say, we want to have in our wave function for different distances between the two hydrogens. Again, okay? So the blue one on top is the one at equilibrium, okay? There we see if we do an energy profile as a function of the spin, then we see, as a matter of fact, that the minimum is really at zero, right? So there's no reason to break the symmetry there. It's very happy in a spin symmetric state. However, if we go to the Coulson-Fisher point, which I think is green, the curve becomes very flat. And if we go beyond that to the purple, brown, and I think cyan or turquoise figure, you see that a minimum at a spin non-zero starts to emerge, right? So it becomes beneficial then to include those particular solutions that with that particular spin broken system in the same way that Burton and Thom had done in their holomorphic Hartree-Fock. So we do that then in a Hill-Wheeler approach. in which we basically expand our system into a whole bunch of constrained Hartree-Fock solutions at this certain spin that we want to include, not being restricted to restricted and unrestricted Hartree-Fock. Okay, so that's the game that we play then. This Hill-Wheeler, so and the results you can see on the right-hand side. So there's a couple of figures there, a couple of lines there. So the one that we're after is the dashed one at the bottom. Unrestricted Hartree-Fock is the blue one, and our what we call NOCI, NOCI, because it's a non-orthogonal configuration interaction. Basically, the green one is the one that we're interested in. Basically, gives us the amount of correlation that we want. This one, the first one was for 1.4 dissociation before the Coulson-Fisher. Actually, this one is beyond, and we see a similar behavior there where it allows us to capture the correlations. Okay, I think I am running to my end, so I'm gonna go to my conclusions. So I hope that I, let's say, I've convinced you that putting in constraints or having a constraint or a Lagrange multiplier here and there to tune your wave functions or to tune the observables in your wave function is a powerful tool, because it opens up a dimension in which you can study problems that have occurred in other theories or in other methods. So most in particular, we were able to investigate where the delocalization error comes from in density functional theory or density-based approaches. Whoops. And we can also use it to our advantage to construct, let's say, basis functions or basic configurations that are in line with the physics that needs to be included in the wave functions that we're after. So that being, this brings me to my very last slide, in which I would first like to show you people from the West how beautiful our campuses up in the East can be, and also my funders, the Canada Research Chair Program, NSERC, NBIF, and obviously also University of New Brunswick for a starting grant. So thank you for your attention. Do you have any questions for me? Are you still there?
Yeah, thank you. Thank you for the talk. And I guess let me know who has questions by, yeah, Marcel, please. Can you unmute yourself?
Yes, and I can also get my video going. Yep. So, Stijn, nice talk. Nice to hear you. Some of the topics is actually quite nicely related about the partial charge and this final topic. So let me phrase my question in terms of your last slides, where you kind of modify this Hamiltonian H and you add lambda s squared minus s times s plus 1, something like that.
Let me go there.
Yeah. Right. And so if I look at your Hamiltonian for a given value of lambda, this Hamiltonian commutes with s squared.
Exactly.
So let me phrase my question, because then I get to where I want to be. So my guess is you tune the lambda value such that, again, states of different spin symmetry become degenerate. At that point, they can be mixing, because it can be any linear combination is also an eigenstate, and so you can create eigenstates that are not eigenstates of the Hamiltonian, but they are eigenstates of this thing for this particular value of lambda.
Yes, exactly. Yeah. So this is an artificial Hamiltonian. You're totally correct.
Right. But it's again this that you get to this point where so here the thing is the symmetry breaking is confusing, because this Hamiltonian still commutes with s squared, and so it's the degeneracy that allows you to change the spin. Right.
It's a very good point. Marcel. So it's a little bit peculiar here because S squared and the Hamiltonian, as a matter of fact, they commute. However, they do not at the Hartree-Fock level. And here we are after the Hartree-Fock solutions that are broken.
Right. I'm
So
basing that. You use this Hamiltonian to solve the Hartree-Fock equation.
Yeah, so we're explicitly breaking it. You see, so we're the lambda parameter. So the Lagrangian multiplier is actually is negative. Okay, and that allows us at some point the spin Hamiltonian becomes much more important, right? And then you're right. So you have then this symmetry. You have this, and it's a different. Yeah, okay, it's a little subtle, but then
right,
the
right.
spin,
So then because it's in the partial charge. So I was thinking about actually the first chart you do the H2 plus system, and I'm thinking, you know, why is this curve flat? In that you say the partial charge can be anything in the H2 plus system, and it's,
that's right.
again, it's because the sigma g and the sigma u orbital are degenerate in this limit of infinite separation, and at that point I can mix them any way I want, and so I can make the charge in this H2 plus system
Exactly
anywhere I want.
Yeah,
And
exactly.
And you use the same thing where you have this plateau of the lambda, where you kind of create that degeneracy.
Exactly.
And once you have the degeneracy, you know, you can make the charge anything, anything you want. And so I thought this is the same, but here it's actually different. And so if
it's a little, yeah, it's a little more confusing, a little more subtle here, because as a matter, if we do this at the CI level, we would see
that's what I'm starting to think.
Two commuting blocks, and then we would just have, let's say, like the Hamiltonian, the original problem, and then there's like the spin that would sort of like cruise through that, and then it would just like be an integer optimal, like a discrete optimization problem, right? So as soon as they become together, then there's a mixing, and then suddenly we just sort of like flip to the through the spin state.
Exactly, and so you can just kind of pull these two states through each other that are actually not changing, and so that looks like a useless type of thing to do.
What?
In the CI picture, it looks useless.
Yeah, exactly. Yeah, and so in the full problem, it is, as a matter of fact, useless, right? But what we want to have is we want to find those states, that those unrestricted Hartree-Fock states, because then we want to use them in a non-orthogonal configuration interaction spirit, that have those broken spin symmetries of unrestricted Hartree-Fock, right? So that good energy states there, we want to have those broken symmetries, we want them in, right? So, and then what you see is that those systems, they would interact with each other, and you see this level repulsion there. So you can really see how it goes from the spin symmetry to the restricted to the unrestricted there, right?
And so I can understand that your energy becomes lower. Does the property of the wave function become better? Is this close to an S-squared eigenstate?
Is the energy better?
No, the energy is better. I see the green curve, for example, here. But
yeah, exactly.
If you look at the wave function corresponding to this thing, does that have better spin properties? Is that close to singlet?
It's a very good thing. So here it has good spin properties, but in my opinion, that is because it's a very limited problem, because it's only H2. I sort of foresee that if we would go beyond that, it would still be broken symmetry. So then we would have to apply, let's say, spin projection there if you're interested. Well, if you want to lower the energy there further.
Right. Okay. Yep. All right. Thank you for the discussion.
Thanks for your question, Marcel.
All right. Any other questions? I have a kind of, few questions, comment. First of all, I guess one thing to emphasize, that this Hamiltonian that you build by adding the constraint, its eigenstates, sort of the states that you obtain by using approximate ansatz for the wave function, they're not necessarily S-square eigenstates, right? Because all you do is you constrain the average.
So yeah. Well, you are actually, Arthur, is a very good point. But then the thing is, if this would be the full problem, okay, so the exact problem, then what you would have, if I want to have a state with a certain S, okay, with a certain constraint, I have to be extremely precise with my Lagrangian multiplier. I have to be exactly at that particular spot. right?
Right. So because in a kind of quantum computing context, we have a similar construction, and addition of such constraint, essentially you're constraining average of the wave function to be close to the S value of spin that the right function should have, and that could be achieved by sort of a mixing of Ron sort of spin states. Just on average, it will converge. But then you have also, of course, Hamiltonian that will probably try to get this linear combination closer to eigenstate, and we know that eigenstate is sort of an S-square eigenstate, so they share eigenstates. So in that sense, this trick works. Yeah.
So you should be able to. Yeah.
Right. Okay. So then, just from practical perspective, this generator coordinate method, you sort of scan with the approximate ansatz your energy versus spin value or average of the spin.
Yeah, so this figure is a little bit how would I say? So it's a bit of a coincidence that I like this figure, because what is being done here is that you typically do like the holomorphic Hartree-Fock, in which you take restricted Hartree-Fock and one other state. Okay. Now you can categorize that one other state by the average spin breaking, okay, that this state has. So you can parameterize that wave function now by this average S squared of this additional one. But yeah, so you get there. It's not really, yeah. So this is really like the outcome of a NOC then for H2, okay, back on the back of the envelope calculation, as a function of the spin contamination that is coming from the broken symmetry state, right? And this is the thing, by means of the Lagrange multiplier, we can tune how much we can put in there, right?
Okay, and so regarding this calculations with the UHF mixing with RHF restricted with unrestricted Hartree-Fock, so I would imagine, since unrestricted Hartree-Fock has a Ron spin, and mixing it to the RHF will have generally a Ron spin, yet you getting the good energies. Is it just because the system is relatively small, or?
So here you're, yeah, this is one of the typical things with H2, right? Here the system is small, and just by coincidence, because, well, not a coincidence, just like a mathematical thing, because it's only a 2-electron problem in H2 and blah blah blah. It has good spin, right? But this is not to be expected when you go to higher systems, right? So then you'll if you want a good spin, then you'll have to do some additional things, right? This is also a problem is known from nuclear physics. So this is a method that this Hill-Wheeler thing is something that I learned when I was a nuclear physicist. Typically, this is the process, right? So you make a generator coordinates, you break a symmetry, you apply the Hill-Wheeler, and then you project. So in all these 3 stages, you're able to lower your energy towards experimental. Here we don't have to do the final one because it has, by coincidence, it has the good spin.
Okay, and just the last short question. It's probably I missed, but what's the definition of generator coordinate?
Oh, I didn't explain too much. What's in the name, right? So,
what is the exact definition of that?
The exact definition is this one: is the Hill-Wheeler, right? So you identify a broken symmetry. In this particular case, is the spin, okay? And then you create a manifold over constrained Hartree-Fock calculations over that order parameter. That is the exact definition of Hill-Wheeler. And then you solve this problem as a, just you plug this in the Schrödinger equation and you solve.
But is there one-dimensional quantity that we can call generator coordinate?
Yeah, you can do it in multiple dimensions if you wish. The generator coordinate is the order parameter.
Okay, cool. All right, we have a few other questions. Amar Dutta would you unmute yourself?
Thanks for a nice talk. I have a naive question, being a naive experimentalist, so please. it looks like it's reassuring that some of these properties like spin and charge are restored with your methods. But could you please help me understand, do these methods also give you better predictions for energy compared to other methods? Do they give you better predictions for things like transition dipole moments and such?
It's a very good question. So we have not really so I broken down my presentation in two sides, into two parts. So the first one, we use it as an analytical tool, and so let's say my answer is as an analytic tool, I would not use this approach now with this Hamiltonian to do any electronic structure calculations. Where is it? I'm looking for it. I'm sorry. Right, this one up here. No, I'll be specific. Up there, right? Because basically you're complicating stuff even more, right? So the one that you wanted to solve initially is H cool. It's a Coulomb Hamiltonian, and I'm just complicating it a little bit more. I just want to put. I want to tune my system such that I'm in a regime in which I can say something about potential, let's say, places where other methods have no control over this and fail. Now, that being said, the good thing about this, and this is actually like a, how would I say, a second order thing, is what we have now is we have new data. Let's put it this way. So we don't have a new method to do all systems that we want to treat. No, we have like new data on a new kind of system in which the system is a little bit more constrained. So it's a better test for those methods that approximate methods that can now go back, because this one is pretty sophisticated, is pretty computationally expensive, right? We really wanted to have the exact calculation, no approximations there, right? So this is definitely not the way you want to go. But if you can tune if you can optimize your methods now to those sort of things, let's say you can fit your density function theory now to this method, to this data, then you can potentially, you can improve your functional, for instance, to not run into those fractional dissociation problems anymore, right?
And
again,
if you don't mind, just to kind of clear up my ignorance, these fractional charge problems that you mentioned, are they sort of aesthetic theoretical problems, or do they interfere in the calculation?
Well, yeah, okay,
properties?
good point. It's a computational thing, right? So it induces all sorts of errors, and I'm not an expert here, but like we know of a few things, like for instance, band gaps in density function theory are typically mispredicted, which is also related to those delocalization errors. And if we can get a better handle on that, then we can potentially fix those, right? So experiment is what experiment is. It's what the computational chemistry is. The computational packages can provide them. So yeah, this can potentially help in fixing some deficiencies.
Thank you very much.
Actually, I can give a little comment here. So after we published this work, there was, I think, DeepMind who published. So they had done some machine learning, so functional fitting by means of machine learning, because everything's machine learning nowadays. And I had a little conversation with them on Twitter. It's like, oh, it's cool, we have this data, and maybe, well, how does it perform? And their answer was like, yeah, here's our repository. Should be easy to do it for you. It's like, yeah, thanks. It's your functional. It's not mine.
Okay, Marcel, do you still have a question, or?
Yes, I have another question, and it's actually precisely about this fractal charge thing.
Mm-hmm.
And so it's a bit of a complicated question, so bear with me, Stijn.
So,
Purdue, when he kind of talked about this linear behavior and that it kind of is straight lines between integer charges, he really used the ensemble argument. And I think it was crystal clear. This is kind of how you can think about it to get these kind of partial charges from a statistical mixture. Now, your system is very different because you are creating again this degeneracy such that you can create in a single state a partial charge. And so you don't have a statistical mixture, you have a single state by adding a Hamiltonian. So I think these systems are really different.
They are different. They're a little bit different. Yeah, that's right.
And so the question is the system that you created, is it relevant for this problem in DFT? And I don't know the answer at all to that. I'm just raising the question.
I'm going to be honest with you, Marcel. So we've within our group, we've been like swinging from one side to the other as well. Okay, because our Hamiltonian is different. Okay. Right. In the end, what we do is, well, I'm going to answer. One answer to your question is the following. So Purdue, basically, I mean, with all due respect to Purdue, but basically it was just an averaging out, right? So you call it an ensemble, and you just take independent density matrices. Okay.
Right.
Now, if you look at what we do, so we take a full wave function, and then and I think you can sort of see it up here. There you go. And basically we treat the other side as a bath for the first side. So basically what we do is we trace out the bath states in some sense, right? So we're also creating a density matrix, right? And in such a way, and this is what not our critique, but what we wanted to investigate this problem is this works when the system is totally dissociated, right? And we wanted to know whether we can get that behavior, whether that's a phase transition at infinite dimension, let's say infinite dissociation, or if we can work our way towards it, right?
You know, actually, this raises a very interesting possibility, because you could calculate the partial trace of this thing and calculate the states, the eigenstates of or the natural states at system A, and do they refer to the actual systems of the pure Hamiltonian? I guess not. But well, in the level of if it's totally degenerate, they probably do. And then you get from the reduced density matrix, you get the states of the actual system, which are exactly the statistical states that would get into the statistical mixture.
Yeah, so this is one of the pictures that we also have, is that you have like a set of states on the left for A and a set of states for B, right? So there's also this picture that I have that I gave you, right? And as long as this is
right, but your wave function, you can do the Smith decomposition and analyze the states that are purely localized on A, and they may correspond to eigenstates of the Hamiltonian on A that are precisely of the type charged or not.
Very insightful question again, Marcel. And as a matter of fact, it's that we did, and it's also something you notice is that we only given data or results from 4.5. So those are the regimes in which we are sort of certain that we're doing sufficient independent mixing, and let's say that they see the other states only when the degeneracy comes up. You know what I mean? So if they approach too much, the picture becomes a little bit smudgy. Okay. I wasn't too so I mean, you can still find them, right? So you can still see which states are mixing up with what states, and that's cool, that's good. But let's say my chemist colleagues were a little bit less confident in assigning those things in terms of like localization, right? So as soon as here we have nice basis sets, one are localized on A, the other one are nicely localized in B. We have our systems, they mix up, and then we create degenerate states, and we can make that happen. Which is also the reason why these plateaus or these stairs are very crisp, right? So if you would bring them together, you'll see that they wash out, and at some point,
right. And you see some of the curves that are more gradual, not so step.
Yeah, these typical S-shaped things, right? Where you sort of like pour everything in from one bucket into the other, and the buckets are both almost together.
All right, I think it clarified quite a bit what's going on. Nice discussion.
Thanks for your questions, Marcel.
Yeah, I only have a little follow-up on what I guess Marcel asked on the difference between your approach to Purdue linearity, linearity between the different charged forms and your approach. So I was a little bit surprised that you start looking at the dissociation, while I think you could have the same linearity if you just let's say take a single fragment, single molecule, right, and then start increasing its charge from the one integer value towards another, using the fractional essentially charges that you can introduce in the kind of calculations, right, at any level. So you don't need a second fragment. You don't need a separation. You can make the system really simple. It's a one fragment where you just dial up the charge from the, say, 2 to 3 in the case of hydrogen, for example, right?
But how do you do a calculation, Arthur, for a system with 1.1 electrons?
There are ways to do it.
How? In DFT maybe, but not in a conventional quantum.
Not in a wave function
or Constraint.
Yeah.
In a wave function, maybe it's difficult, but in DFT, definitely.
Yeah, no problem, right? So in DFT, you can produce these figures because you put a constraint there, right? It's the same thing, right? So it's you put a constraint on the density, and you can make that value, and you can give it anything, right?
Right, but that's pure DFT. If you do Constraint, you have a bit of an issue with the orbits that are occupied or not. Or you have to make some decision. I'm just going to stick 0.1 of the highest orbit occupied orbit or something. Yeah, I guess you can do that. That's what you do, probably. Okay.
Or essentially some modifications, or some rotations of the wave function that doesn't change the charge essentially, right? But keeps the total charge the same.
I like this is cleaner. You have a definite total number of electrons, and it's integer, and you just say, how much sits on side A or B.
Yeah, I think you need a bath. I think really you need a bath to allow for that exchange in a wave function theory. I think you really need to do it. This is also the reason why there's no issue with the 2DM. So this is the original problem, because there one of the constraints is that to be unrepresentable needs to be the number of electrons that you want. You do like a trace on something, right? And you require that to be such and such. So then we can produce this blue curve, which is an energy profile as a function of whatever number you want to have, even on a closed system, right?
Something on the side, Stijn. Are you familiar with the work of Troy van Voorhis?
Yeah. He's doing
because they do very similar things.
Very similar things. I know.
Right.
I know.
I did see it in your talk, but
yeah, no, I didn't mention it here. It's the generator coordinate method is very. I mean, it's not a new idea. I think I stole it from nuclear physics. But Troy is actually, so the places he's using it more for like conical intersections, those places.
Exactly.
Yeah, to resolve those. It's a similar idea. You take, you find good configurations, and then you mix them together.
Diagonalize over the two states, or create even non-adiabatic representations.
Yeah, and you have but the crucial thing is here you have a knob to choose. I'm not saying that the spin is going to be the ultimate one, right? I don't. For dissociation, for instance, this is a good one. Now, if you're looking into dynamic correlation, let's say you want to use it for that for some reason, maybe you want to do that, then the spin is not going to get you anywhere. Then you'll need another one, right?
Right.
All right. Thank you. Do we have any other questions? If not, let's all unmute ourselves and clap properly to thank Stijn for great talk.
Yep.
Thanks a lot. It was great to be back at U of T.
Yeah.
Thank you.
I enjoyed being there too.
Next time is
easy.
Yeah. Thank you. Take care.
Thanks a lot, Arthur. I have to go because I have to teach now.
Okay.
And